Hello everybody, this is Mikhail Porosyan from AUA with Probability Lecture 30. Today we're gonna talk about jointly continuous random variables and joint PDFs. And as a supplementary material, I will talk a little bit about conditional distributions. So before beginning, some notes and reminders from Calc 3 from multivariate calculus. So first note on notations. For points in R2, I will usually write in two ways. So either I will write the point xy is in R2, or I will write just the coordinates x and y are in R. And if I want to describe points in a rectangle, so if I want to describe the rectangle AB times CD, so this is Cartesian product, and if I will draw that rectangle, I will have the following. So AB, so x is from A to B and y is from C to D. So this is our rectangle. So if I want to, this is our rectangle. If I want to describe that rectangle, then I will write either xy is in that AB times CD, that Cartesian product. So my point xy is here, or I will write just the x coordinate is in AB and y coordinate is in CD. Okay. But please note, this is important and common mistake students are doing. Please note that if we want to describe, say, the open unit disk D, so this is a disk with center at the origin, so this is the center in our case, and this is the radius one. Let me draw that. So if we want to describe the unit disk, so this is our region now. In this case, this point is 1, this point is -1, this point is -1, and this point is 1. So I will write either, so this is D. I will write either xy is in D, in that region, or I will write the disk points equation, so x squared plus y squared is less than 1. All points of this disk are satisfying this, and all points satisfying this are in that disk. But writing in this way, so writing x is from -1 to 1 and y is from -1 to 1 is incorrect, because in that case, if I will write in this way, then I am describing the whole square of this form. Whole square. So I'm describing this red boundary part region. If I want to describe in another way, so I can write in the following way. So I can write that x is first describe my disk in terms of x, first x. So x is from -1 to 1. And then I need to describe for any x, say if this is x, I need to describe where y is running. So y is running from this point to that point for that fixed, say this is x, this point is x, and I am describing where y is running, and y will run from -square root of 1 minus x squared to plus square root of 1 minus x squared. Where these formulas are coming from, so the formula for the boundary is x squared plus y squared is equal to 1. So I'm solving for y. In the upper part I'm getting the square root with plus sign, and in the lower part I'm getting the square root with minus sign. So this is the correct way to describe the points inside that unit disk, but this is incorrect. Okay, so let's move forward. We will use level curves. Sorry. So just a quick reminder on level curves and geometric interpretation. So assume we have a function of two variables f of x and y, and we want to draw the graph, we want to visualize, we want to see what is happening with the graph of this f. The graph will be a surface in three-dimensional space. So sometimes drawing is not so easy or not helping to see some to draw some conclusions or do calculations, and then we are using level curve map or so-called contour map. And what is the level curve? Assume L is any number, any real number. So L is the level. We are solving this equation, and all points, the set of all points satisfying this equation is the L level curve. So geometrically, L level curve is the set of all points of the intersection of the surface z is equal to fxy. So this will give the surface of f in three-dimensional set. We are intersecting that with the horizontal plane z is equal to L. So plane with height L, horizontal parallel to x or y plane, and the intersection with the surface of this z is equal to fxy. And this is the visualization of that. Say the surface of fxy is this yellow one, or orange one maybe. And I want to find L level curve for this surface. So L, I'm taking L is equal to 0.05, and then I'm taking the plane which is parallel to x or y. So this is x-axis and this is y-axis, or this is y-axis. So this is y-axis and this is z-axis. So I'm taking this point 0.05 and I'm taking a horizontal plane passing through that point. So this is that plane. And I'm finding the intersection set, the set of all points on the intersection of this plane in blue and this surface in orange. So this will be the set of all intersection points. And next, to calculate, this is not yet the level curve. To find the level curve is in 2 dimensions. We are projecting this. So I'm calculating the projection of this on the x or y. And I'm just leaving this red. And this is the L level, in our case 0.05 level curve for our function fxy. And of course we are representing that in the x or y axis as usual. So this is that level curve. And usually we are writing on this curve the level for which it is calculated. So we are writing L is equal to 0.05, or just we are writing 0.05. Okay. Say if I will give the following contour map or level curve map to you, say I am doing the following. Say I have a function. Here my function is 1, and say here my function is 3, so 3 here, and 0 outside. So I'm giving this in two-dimensional set, but I'm describing the level curves or contours of that function. In fact, what I'm giving, you need to visualize this as the following. Let me try to do that in three-dimensional space. So this is x, this is y, the same x, y, and this is z. So here I am describing the heights of that surface. So what I have here, I have that portion of that circle, say, and over that portion, over this region, I'm drawing a surface with height 3. So I'm taking, say, 3, this is 3, and I'm doing that surface. Let me try. So I'm moving this horizontally, parallelly to the height 3. So this is 3. I will get something like this. Okay. Then I am taking that portion of rectangle, so something like this, parallel to this axis, parallel to that axis, something like this. Okay, and over that I'm raising this, in fact raising this rectangle to height 1. So I will have parallel to that with height 1, something like this. So this is another portion of my graph with height, say, passing to 1. And everywhere else, so at this portion, I will have 0. So my surface is lying on the plane x or y. So everywhere here, besides this portion and that portion, my surface is on x or y. So hope this helps. This is the way we will visualize three-dimensional surfaces sometimes during our lecture. Okay. Another important thing is being able to calculate double integrals, and this is a quick reminder on how to do over the double integrals over some simple regions. And also I will give the change of variable to pass to polar coordinates. So assume we have a two-dimensional region D, so D is in R2, and we have an integrable function defined on that D. And we want to calculate the integral over D of f. So assume D has the following shape. So D is bounded between the curves y is equal to h of x, this red curve, and y is equal to g of x, this black curve, and x is running from a to b. So this is our D, and we want to integrate our function f over this D. To that end, we are doing the following. So we are writing this integral in the iterated integrals form. So we are describing our region D in the sequence, say, first x, then y. So what that means, first x means, first I am describing where x is running for the points, if I am taking a point inside that D. So x is running, of course, from a to b. So I'm writing integral from a to b dx because I'm talking first about x. Okay, so x is running from a to b, x is anything, so I'm taking that x. So I'm considering now all points with the x coordinate x. Now, which portion of that points, so for which y, the points x, y will be inside our region D. So if I will draw this portion of all points with x coordinate x, so I will have this part, and only this portion is inside our D. And how can I describe that portion? This point is, well, if this is x, so this is h of x, and this is g of x, because the equation is given by y is equal to g of x or x. So my my y will be between h of x and g of x to describe the points in D. So I'm integrating, so I'm writing for y from h of x to g of x, the integral of our function f, the same function, but with respect to y. So first I'm calculating this inner integral. In this integral, y is the only variable, so x is constant, x is fixed, x is fixed, x is fixed. I'm integrating with respect to y and obtaining some function in general depending on x. Then I'm integrating that function from a to b with respect to x. So this is the method of iterated integration. Okay, so sometimes we have this kind of region D. So what is this kind mean? What that this kind means? So we need to separate. We need to separate our integral into integration over two regions. What is the difference between this and that? So here the lower part of our region is given by one equation, say y is equal to h of x, but the upper part of our region is described with different functions over different regions. Say from a to c, this is c, from a to c the equation of the upper part is y is equal to g1 of x, and if x is running from c to d, the upper part is y is equal to g2 of x. And in this case, if we want to integrate our function f over that d, we can divide that d into two portions. So this is the first portion, this is the first set, and this is the second set. And because integral is additive, and that means so the integral over d can be decomposed into the integral over this d1, say, and integral over d2. If we will do that, I will obtain the following. So the integral over d of f is, first I'm integrating over that first part, left part. So left part is x is moving from a to c. So x is moving from a to c dx. And for each fixed x, if I will fix x here, my point is moving from h of x to g1 of x. So y is moving from h of x to g1 of x. fxy, the same function, and integrated with respect to y. This part will give integral of f over this region, and the next part is for the left part of our region, and that is given by integral from c to b. So x is moving from c to b, integral cb dx, and for each x between c and b, y is moving from h of x to g2 of x. So integral from h of x to g2 of x of our function f with respect to y. So we are calculating this inner integral, obtaining function of x, plugging here and integrating with respect to x from cb. And similarly, we are calculating this, and that is giving our integral we wanted to calculate. Now, if our region D or our function maybe and our function f is easy to handle with polar coordinates, then say we have function which is radially symmetric, say it has x squared plus y squared in it, etc., then we can make a change of variables in our double integral to by passing to polar coordinates. So to that end, we are doing the following steps. We are using x is equal to r times cosine of phi and y is equal to r times sine of phi. So these are our polar coordinates. Next we are describing, this is important, describing our integration region D in terms of R and phi. And we are denoting D by D tilde the region in the R phi coordinate system. So what I mean by that, let me show. Say we have this kind of, so this is X, this is Y. I'm describing D, the integration region D. Say we have this kind of shape. So this is our D. This is our D. And here, say I have 2 half circle with radius 2. So I need to describe the same D, this region, right region, by using R and phi. So I can do the following, say describe first in terms of R, then in terms of phi, or I can describe first in terms of phi, then in terms of R. Let me do, in this case, this is not, the order is not so important. Let me do first in R, then in phi. R in this region, R is showing the point xy distance from the origin. So R is the distance between xy and 0, 0. So in our case, in the region, R is changing. Radius of all points in this D are between 0 and 2. And if I am fixing all points with radius R, so say this is R, all points of radius R will form this portion. Well, sorry, yeah. This half circle with radius R. Then I need to describe where my phi is running inside that region D. So for each R here, phi is running from 0 to pi. So 0 to pi. So if I will give this description in the R phi system, coordinate system, then I'm describing the same half circle. I'm describing the same D. So this is our description in the R phi system, for coordinate system. So this is our D tilde in this case. So that is our D tilde I'm talking about here. Okay, so let me erase this. Next, we need to calculate, we need to remember to calculate the absolute value of the Jacobian, which is R in the polar coordinates case. And we are making the change of variables. So what are we doing? This was our integral we wanted to calculate over d of f, the double integral over d of f, and we are writing it in the r and phi coordinate system. So we are double integrating over d tilde, our region, in terms of r and phi. We are plugging here, instead of x, the value of x, so r cosine phi. So instead of x, r cosine phi. Instead of y, r sine phi. Then we are remembering to write the absolute value of the Jacobian, which is r in this case, and we are writing dr d phi. We are integrating with respect to r and phi. So this is the polar coordinates form of our integral. Polar coordinates transform of our integral. Okay, this much. Now let's talk about jointly continuous random vectors. And first we will consider, and mostly we will consider, two-dimensional case, and at the end we will just quickly give the method to generalize for n-dimensional, general n-dimensional case. So we will talk about two random variables, x and y, and we will consider the case when x and y are jointly continuous in our lecture. Okay, let me remind that last time we considered that following cases can happen when we are dealing with two random variables. So we can have that x and y are discrete random variables. In that case, we are talking about jointly discrete random vectors. And now we will talk about the case when x and y are jointly continuous random variables. But we can have also other cases, say x is discrete, y is continuous, or vice versa. One is discrete, one is continuous, or we can have other cases also. So last time we have talked about this discrete case, and today we're gonna talk about this second case. Okay, so first let's recall the definition of continuous random variable in one-dimensional case, in the case when we have one random variable. So x is a random variable. We say that x is absolutely continuous if there exists a non-negative integrable function f called the Pdf, such that the CDF of random variable x is the integral of that Pdf over minus infinity to x. And this works for any x from R. And our Pdf is a function satisfying these two conditions, these two properties. So Pdf is non-negative for any x, and the integral over R real line of our Pdf is 1. And if we have a function satisfying these two properties, it is a Pdf for some random variable. Now we are defining continuity of random vectors in the similar way. So we say that the random variables, I need to erase one of these. So random variables x and y are jointly absolutely continuous. We will say just jointly continuous if there exists a non-negative integrable function f. I define it on R2 such that the joint CDF, we know the definition of joint CDF. The joint CDF fxy is the integral of small f over minus infinity to x times minus infinity to y. And this works for any xy. So let me just quickly recall the definition of joint CDF. So joint CDF is, well, fxy is probability that our random variable x is less or equal than small x and y is less or equal than y. So if we can write this function in the form of this integral, then we say that random variables x and y, or which is the same, random vector xy, is jointly continuous. Okay, and we are calling this small f to be the joint Pdf of x and y. And if we want to specify that f is the joint Pdf for x and y, we are writing in the index that x and y. So again, our joint CDF is the integral of joint Pdf, integral over this region. And similar to one-dimensional case, in the following properties of joint Pdf can be proven. Double integrable function f is a joint Pdf of some random variables x and y if and only if the following two properties are taking place. So f is non-negative for any UV, and the double integral over the whole plane over minus infinity times minus infinity plus infinity times minus infinity plus infinity of f is 1. So geometrically that means that the volume under the joint Pdf surface, so we will have a surface for that fxy, the volume under that joint Pdf surface is 1. And if we have this if means if and only if. Say if we have a function satisfying, integrable function satisfying these two properties, then there exists a random vector xy behind that such that the joint PDF of xy is exactly that f. Now, relationship between joint PDF and joint CDF. The relationship, one of the relationships is given through the definition. So if we have joint PDF, small f, and if we will integrate that small f from minus infinity x times minus infinity y, so u is running from minus infinity to x and v is running from minus infinity to y. If we will integrate this, we will get joint CDF. This was the definition of continuity of random vector. Now, if we want to calculate small f joint PDF having the joint CDF f, we are just differentiating. If we will calculate this mixed second order derivative of joint CDF, so d2f with respect to dx, then dy, this mixed partial derivative will give joint PDF. And this works for almost all points xy. At some points, our joint CDF can be non-differentiable. So this holds for almost all. Now, how to calculate probabilities using joint PDF? Recall that the main aim, one of the main aims of our jointly distributed random variables was to be able to calculate probabilities like this. So probability that xy, that point xy is in some set A is in R2. Say, I want to be able to calculate this kind of probability. Say this is A, and I want to calculate, this is region A, and I want to calculate what is the probability that my point, random point xy will be inside that this region. And having joint PDF is a very handy tool to calculate this kind of integrals because of the following formula. So if we want to calculate the probability that xy is in A is in R2, we are integrating, double integrating over that A, our joint PDF f. So this is the analog for one-dimensional case. So let me recall that for one-dimensional case, this is x, this is y. If we have some PDF, say this is PDF of one random variable x, and if we want to calculate the probability that sorry, the probability that our random variable x is here, so probability that x is here, we are integrating probability that x is in, say, AB, then we are integrating our PDF, say our PDF is f, we are integrating that f over AB, over that set. In this two-dimensional case, if we want to calculate that point, instead of x we have random vector xy, that x is in that set A, we are double integrating over that A, our joint PDF. So straightforward generalization. And recall that this integral, I can continue from this point. So this integral geometrically means to calculate this area. So area of that shaded part. Area of this shaded part in one-dimensional case. In a similar way, if we will talk about two-dimensional case, we will have first let me write this formula for ABCD. So if I want to calculate the probability that this is the same as to write my point xy is in the rectangle AB times CD. So this probability is just the integral over this rectangle of joint PDF. So, and integral over this rectangle can be written in the iterated form as integral from a to b. So I can write this in the following way. X is running from a to b dx, and for each x, my y is running independent on x. My y is running from c to d. So c to d f, say x, y, dy. Okay. Now, what I wanted to show is the geometric meaning of this. So what we are calculating with this integral and with this probability. In one-dimensional case, we are calculating the area under the joint PDF curve, and in this case, the probability that xy is in A is equal to volume of the body under the surface of the joint PDF graph over the region A. So if we want to find the probability that xy is in A, we are calculating the volume under the joint PDF. So let me give the graphical description of that. Say this is our joint PDF surface, x-axis, y-axis, and assume we want to calculate the probability that xy, so our random vector xy, so this is x-axis, this is y-axis, y-axis. So xy is in A, and A is this region. So this region, that blue region, is on x or y-axis. So the projection, this x or y-axis, has the following form. So this is our A. This is the picture in three-dimensional space. So I want to calculate what is the probability that my random point xy is, random vector xy is in this set. So what we are doing is the following. So I'm constructing the portion of my surface over that region, and I'm calculating the volume under that portion of the graph of that surface. So I'm calculating the volume of this three-dimensional body, and that volume will give, so this volume of this is equal to the probability that xy is in that base A. A was the base for this body. Okay, and this is the surface z is equal to fxy. Okay, I will use this geometric ideas calculation of volume to calculate some integrals. So let's move forward. Now, using that idea, we will have the following. Recall first that for one-dimensional case, say we have one continuous random variable x, the probability that x will take that particular value a is some fixed number, this probability is 0. In a similar way, if we have that x and y are jointly continuous, then for any fixed point ab, the probability that xy will take that particular value ab, that is the probability that x will be exactly a and y will be exactly b, this probability is equal to 0. So we can say, but in this two-dimensional case, we can say even more. If we have a set A in R2 which has a measure or area equal to 0, so area of A is equal to 0, then the probability that xy is in A is 0. For example, if A is some nice curve, say if A is, this is x, this is y, I'm not drawing the surface of f, I'm not drawing in 3 dimensions. Say I have this kind of set, this is my A. Now, what is the probability that my point xy is in this A if x, y are jointly continuous? So in this case, this probability is 0, because I need to calculate the volume of the body over this set and under the graph of f. And that volume will be 0. In particular, if xy, that pair xy, is a jointly continuous random vector, then the probability that x is equal to y is 0. Why is this? Because we want to find the probability that our point xy is, this is the line x is equal to y. So if I will denote this by a, this line is our a. So we are calculating what is the probability that xy, our point xy, is in that line. This is the same as to write it in this way, if a is our line. And because the area of this line is 0, then the probability that xy will be in this a is exactly 0. So for any jointly continuous random variables x and y, the probability that x is equal to y is 0. Okay. Now, what will be the possible? What are the possible values generated from random vectors? Let me just quickly recall one-dimensional case. Say if I have this kind of graph for our PDF, one-dimensional PDF, say something like this. So what is saying this PDF of x, PDF of some random variable x? What is saying this PDF about our random variable x? So it is saying that my points, if I will generate points from x, the values of x cannot lie here, because the probability that my x will be here is 0, or probability that my x will be here is again 0. So x cannot take values here. X can take values here. Most probably our x will be here, because the probability that x is here is given through this area, and that area is close to 1, because the total area needs to be 1. Okay, so this shape is giving information about that random variable x. And similarly, for two-dimensional case, random vectors case, the shape of PDF is giving everything about that random variable x. Say here in my graph, f is fxy, the surface of fxy is 0, so the values are 0. So that means that my random variables xy cannot take values in this region. So they cannot be in this region, and then they cannot be in this region because f is here. They cannot be here. Okay. Most probably the values of xy, that pairs, are in the under this bell things. Well, under these mountains or at graph things. So now in the next slide, I am generating some thousands of points, possible values of xy pairs, and that possible values are mostly here and there. So let me show that. So I am generating points. Yeah, you can see that mostly that points xy are here or there, corresponding to that mountain shaped things. Okay, so what is this? This is just one of the possible values of xy. What is this? This is another possible value of xy. So we have generated several thousand points, possible values of xy. So dataset generated from the previous joint PDF. Okay. So now this is the graph of some joint PDF. And what I want to do in this case, I want to first generate points from this distribution, and then, so mostly my points, I will not have points here, because here f is 0, here f is 0, f is 0. So my points will be mostly concentrated here, and sometimes they will lie around that peak. Okay, now after that I want to draw the two-dimensional density histogram. So what that two-dimensional density histogram means, let me just quickly give the idea. So if I will generate some points, so I will have something like this, a lot of points. So points, points here. What I'm doing, I'm taking a grid, so I'm dividing into some small squares. Then for each square, I'm calculating the ratio of points in that square. So 1 over the total number of elements, 1 over the total number of elements. Here I have several points, say 3 over the total number of elements. And for each square, I'm drawing a three-dimensional bar over this square with the height corresponding to that proportion. I'm drawing density histogram, so I'm drawing proportion of points that will lie in that rectangle. Okay, so let me show the 2D. In fact, 3D. Sometimes people are talking about 3D because the histogram will be in 3D. 3D density histogram for this. So if I will generate, the idea is the following. If I will generate points, mostly my points will lie here. So the shape of that density histogram will repeat this shape. So let's see. Yeah. So I have a lot of points around the, say, 0, 1, maybe 1 and 2, around that point 1, 2. A lot of points. Sorry. And I have few points with x is between larger than 4, say, and y is inside, say, 0.1 and 1. Okay. Now let's solve some problem. So the first problem is the following. T is the triangle with the vertices at 0, 0, 1, 2, and 4, 0. So let me first draw that triangle. So what I have, this is x, this is y. So I have point 0, 0, 1, 2. This is 2. This is 1. This vertex. And the other vertex is, this is 1, sorry. At 4, 0. So x is 4, y is 0. And I have the following triangle. Okay. Let me try to join. Yeah. Something like this. And this part also. So this is my T. So what I have next? Okay, F is equal to K if xy, if this point xy is in T, and 0 otherwise. 0 otherwise. So returning to our graph, we have the following. So our F is K at this region and 0 otherwise. 0, 0 outside of this triangle. If I will try to visualize this in three-dimensional case, I will have the following. So x, so I want to draw the surface of my fxy, y and z. I will have the following. So I'm drawing the triangle. Say this is 1, this is 2, 2. I will have this line, this is 0, 0. I will have 4 here, and that line. This is the base, and I'm raising this triangle to the height k. Say this is k. I'm raising that to that k, so I'm drawing parallel thing to that triangle, parallel triangle. So this is a portion of our surface over that triangle, and in all other places, for all other points, our plane, our surface coincides with the plane x or y. So just think we are just cutting this triangle from that x or y, from that plane, and raising to the height k. So this is the graph of the surface f of x, y, f, x, y. Okay, so what is asking our problem? Assume that f is a joint PDF for some random vector x, y. First find k. So let's move to our picture. Find k. How we will find that k? We need to remember that the integral of our f over the R2 over the plane is 1. That is, the volume under that surface of f is equal to 1. And because everywhere else except this triangle f is 0, we will just left with the following volume. So we need to calculate the volume of this prism, so this three-dimensional prism, and recall that the volume of that prism, or let me just write double integral over R2 of our f dx dy is just the volume of this prism, and this is equal to the area of the base, so base times the height, and in our case base is a triangle, and the area of that triangle, so I'm calculating this area of this triangle, the height is 2, so 2 times 4, 2 times 4 over 2, so this is the area of our triangle, area of the base, and times the height is k, the height is k is written here, so height is k, so this h is k. And this needs to be 1, equal to 1. Sorry. So from here, k is equal to, well, I will have 4 times k is 1, so k is 1 over 4. So this is the value of our k. Okay. Moving back to our problem, we have solved the first part. So calculate the probability that x is between 1 and 2. So we need to calculate the probability that x is between 1 and 2. So what I am doing, I'm not thinking in 3 dimensions because it is not so easy to draw and think in this 2-dimensional space, but I am thinking in 2-dimensional projection. Well, I'm talking about the values of x and y projection. Okay, so I want to calculate the probability that x is between 1 and 2 and y is everything, because we do not have y is anything. So x is between 1 and 2, that means, say this is 1, this is 2, x needs to be here and y can be anything. So I want to have my points are inside this strip. But because outside of this triangle my f joint PDF is 0, I just need to calculate what is the probability that my point xy is here. So this is our set A, and this probability is the same as the probability that my point xy is in A. Okay? And I know the formula to calculate this probability. This is the double integral over A of fxy dx dy. Okay, but if I am calculating the double integral of a constant, so this was k, f was k over that whole triangle. So in this portion also over a, the value of f is k. So this is equal to k. I'm writing k times the integral over a of 1, and the integral over a of 1 will be the volume of that part. Well, not the volume, but sorry, I need to erase this. Yeah. So this will be the area of A, because A is 2-dimensional, not 3-dimensional. So this is k, this goes out, and double integral over A of 1 dx dy is the area, is exactly the area of A. In fact, this product will give the volume of this portion of the body. So we are calculating the volume of this portion. So we will have something like this kind of prism, and we are calculating the volume of this prism. And the volume of this right prism is the height, this is the height, times the area of the base, and the area of the base is the area of A. Now, how we can calculate this area? So k is 1 over 4, so we can plug that value 1 over 4, and it remains to calculate the area of A. Going back to this, we have trapezoid here, and the height of that trapezoid, this is the point 2, so this portion length is 1, so height is 1, and we need to calculate this base length. So this base length is 2, the height of that triangle, and we need to calculate this base length. So we need to calculate this length. And how to calculate that? Because we have similar triangles here, so this is similar to that. If I will denote this by this line by L, the length is L, I will have the following: L over this length, and this length is 2, is equal to this over that. So this length is 4 minus 2, this is 2, over this length, and this length is 4 minus 1, so 3. And we will have that L is equal to 4 over 3. This part is 4 over 3, this part is 2, and the height of our trapezoid is 1. So this will give the following: k was 1 over 4 times small base 4 over 3 plus long base 2 over 2 times the height. Height is 1. So this is the probability that our point is in this region A, or x is between 1 and 2. Okay, so let me erase. I'm erasing this. I have yet another thing to calculate, probability to calculate. I will draw that again. So now I need to calculate this probability, the probability that x plus y is less or equal than 2, given that x is less than 2. So probability that x plus y is less than 2, given that x is less than 2. Again, I am starting from picture in 2-dimensional case, so x, y. My triangle was something like this. This was 4, this was 0, this was 1, and the height was 2. Okay, so what I'm doing, first I need to write the equation for this conditional probability. Okay, so the conditional probability can be calculated in the following way. So probability that x plus y is less than 2 and x is less than 2 over the probability that x is less than 2. Now, probability that x is less than 2 is the following. So we are calculating, this is 2. X is less than 2 means x is in this side, and because x, y, our points cannot be outside of this triangle, I need to just mark the part in that triangle with coordinate x is less than 2. So x is less than 2 is this portion. So if I will denote this by A, say again, the probability that x is less than 2 is the same as to write the probability that my point xy is in that A. Okay, I have two methods to calculate. So I can calculate straightforwardly with this A. Well, this is the double integral over A of f dx dy, and because f in this region, and in particular for A, f is equal to 1 over 4, this is constant, I will have 1 over 4 times the area of A, and I need to calculate that area of A. The area of A is easy to calculate by calculating the triangle area. We have that triangle area and minus this part's area, and this is another triangle. We have calculated this. The length is 4 over 3. So we have the height, we have the base, so we can calculate this area and take that part out of the area of that triangle. So I will not calculate this area of A. So you can do in this way, or you can think like this, maybe easier to write 1 minus the probability that x is larger or equal than 2. So x is larger or equal than 2 means we are talking about our point being in this green part. So, and calculating the probability that our point is in this green part, maybe it is easier, but we will be reduced to the same calculations in fact. Okay, so we will calculate this part by using that ideas. It remains to calculate this area. And how to calculate this? Let me erase this part. Okay, now I need to calculate the probability that x plus y is less than 2 and x is less than 2. X is less than 2, that means that we are in this orange part, and now I need to specify all points satisfying this inequality, and I need to find the intersection of this because we have end here. So x plus y is less than 2. First I am drawing the line x plus y is equal to 2, or with small x and y is equal to 2. This is y is equal to 2 minus x raised to 2. So I will have, it is passing through these points. So I will have this line. So, and because we have y is less than 2 minus x, y is less than 2 minus x, we will have the points under that line. So, and in fact, because our joint PDF is 0 outside of this triangle, we will be left just with this region. So all points here are satisfying this inequality. X plus y is less than 2. Let me write that this equation is y is equal to 2 minus x, exactly. So under this means x plus y is less than 2. And we need to calculate the intersection with x is less than 2. X is less than 2 was this orange part. So intersection will give just this this portion. So let me maybe I will take another color. So this is our, say, set B, and this intersection is our B. Now we are asked to calculate the probability that our point xy is in that B. Well, this is again the double integral of f dx dy, and because f is here, f is constant, f is 1/4, so I will have 1/4 times the integral of 1 dx dy over b, and the integral of 1 over b is giving the area of b, so this will be 1/4 times the area of b, and it remains to calculate this area of b. So b is a triangle, we have the base is 2, and we need to calculate the height, and I'm suggesting you to calculate that height. That is not so hard. So the method is the following. So you need to calculate the coordinate of intersection of these two lines. So this line equation is given. You just need to write the equation of this line, calculate the intersection point. That will give the x coordinate of this point. Having that x coordinate, you will find this height. Try to calculate this area and plug into the formula to calculate this conditional probability. Just one note at this point. So let me quickly erase this part and write that note. Maybe I will erase everything. Yeah. So what is that note about? Common mistake is the following. So we want to calculate this conditional, we are given this conditional probability, x is less than 2. We are thinking like this. So this was our base triangle. So 0, 1, 4, this is 2, and we are thinking like this. X plus y is less than 2 means this is 2, this is 2. We are under this. So we are under this. X is less than 2, we are right to this. And because outside of this triangle our f is 0, we need to calculate the probability that our point is here. So let's calculate the probability that xy is in that B. Well, this is not correct because instead of this conditional probability, you are calculating the following probability. So you are calculating the probability that x plus y is less than 2 and x is less than 2, not given that x is less than 2. So please, first, when you are dealing with conditional probabilities, first write the definition of this conditional probability, then separately calculate numerator and denominator. Okay, hope this was clear. Let's move back to our problem. Yeah. So we have solved this problem. The next problem is the following. Our joint PDF of x and y is given by this formula. So what is this formula saying? So f is 0.2 constant over the unit disk centered at the origin. F is another constant k, unknown k, we need to find that k, over this 2, 3 times 2, 4, and 0 otherwise. So let me first visualize it in 2D with level curves, contours, and then in 3D, in this case it is a little bit easy for me, and then we will calculate, we will solve the rest of the problem. So first, this the graph of this in 2-dimensional case and 3-dimensional case. So what I have, this is x, this is y. So first f is 0.2 in the unit disk. So say this is our unit disk. Yeah, radius is 1. So the values of f, let me write in other color, are 0.2 here. Everywhere in this region I will have 0.2. Okay, and another portion here, so that was, let me go back, 2, 3, x is between 2 and 3, y is between 2 and 4. So this is 2, say this is 3, this is 2 and 4, 4 is somewhere here, 4, 2, 4. I will have this rectangle. So in this rectangle, the values of our function are k, so I have constant k here. In three-dimensional case, I will have constant surface, some portion of plane over this with height k, and 0 everywhere else. So let me try to visualize this in three-dimensional case. So what I need to do, I need to cut this unit disk, raise with the height 0.2. I need to cut this rectangle and raise to height k and leave all other points on the x or y plane. So a three-dimensional version of this is the following. So actual graph of fxy is the following. Say this is x, this is y, this is z. So what I'm doing, I'm drawing first that circle, circle, circle in x or y axis, say something like this, and I'm raising this to the height 0.2, so parallel. Yeah, this is the surface. Passing this point is 0.2, so 0.2. Height is 0.2. Okay, 0.2. I have another portion here, so I'm taking that rectangle. So this point is 2, this point is, if I will go 3, this point is 4, this point, not 4, 2, this point is 4. Okay, I'm raising this rectangle to height k, unknown k. So I'm trying to draw this parallel rectangle. Yeah. So this is another portion of my surface, and the height is k, that is passing through the point k. Okay. And everywhere else outside of that unit disk and this rectangle, sorry, our f is 0. So I will have that plane x or y for the surface graph. Okay, so this is my three-dimensional version. Surface z is equal to fxy. Okay, so let's move back to our problem. So the problem is the following. First part is find k. So how I'm calculating that k, I'm remembering that the volume of the body under the graph of joint PDF needs to be 1. So I need to calculate the volume under this surface. So that volume will consist of 2 separate volumes. So I need to calculate the volume of this cylinder with height 0.2 and base area equal to the area of the circle. And another is prism or cuboid, maybe parallelepiped volume. The height is k, that unknown k, and the base area I can calculate. This is easy. Okay, so I'm looking here, I'm not looking here, and I'm thinking about this number is the height raised here. K is height, and the area I can calculate. So 1 is equal to the double integral over R2 whole plane of f dx dy. Okay, this is equal to the volume of cylinder plus the volume of cuboid maybe, or parallelepiped, And this is equal to volume of cylinder is area S of circle times the height of that circle, maybe plus the area of parallelepiped is S of the area of this rectangle times the height over that rectangle, so height of that rectangle, and this is equal to the area of that circle is, we have unit circle, pi times r squared, and r is 1, so pi, times the height is 0.2, so height is 0.2, and plus the rectangle area is, this side is 1, this side is 4 minus 2, so 2, 1 times 2 is 2, times the height of that rectangle is k, is this number written. Yeah. So this needs to be 1, and I'm calculating from that k is equal to 1 minus this over 2. So 1 minus 0.2 times pi over 2. Well, some number. I will keep writing k. The actual value of k is this much. Okay. Now, let me erase that part to solve other problems, other parts of our problem. So no need for three-dimensional case. I will work with two-dimensional contour plot, level curve plot. Okay. So we have solved this. Calculate the probability that x squared plus y squared is equal to 0.5 squared. So even I'm not looking at the graph of this because I have joined PDF, so my random variables are continuous. And this is the curve A. So I am denoting this by A. So this is the same as to write the probability that my point xy is in A. So because the area of A is 0, the area of that curve, the boundary of this circle, the boundary of this disk is of 0 area, so this will be 0 exactly. So no need to do any calculations. Recall that the probability that xy lies on some curve, exactly on that curve, is 0 if we are dealing with continuous random vectors. Okay, so this is easy. Now calculate the probability that x is larger than y and y is larger than x is larger than 0, sorry, and y is larger than 0. Okay, so let's move here. So I want to calculate the probability that x is larger than 0 and y is larger than 0. So I want to calculate that my point is in the first quadrant. And because xy, my points cannot be in this portion, they can be only in here and in this circle, it remains to calculate the probability that my point is in this green region. Okay, so we calculate the probability that xy is in that green region, and green region is this A, region A. It consists of two portions. Well, one is a portion of the circle and the other one is that rectangular shape. So the probability is equal to the probability that my point xy is here, or the point xy is here. So I can separate probability that xy is in rectangle plus, because we have disjoint cases, so probability there's a rectangle and these are disjoint, so xy is in this segment. So how to calculate that? So double integral over that rectangle of our f dx dy plus double integral over that segment of f dx dy. Okay, and how to calculate this integral? Because over this rectangle, our function is constant, so f is equal to k, we know the value of k. Now this is just k times the double integral over rectangle of 1, so k goes out of 1, and the double integral of 1 is the area of rectangle, and this area was 2. Plus f is constant also on this segment, this part, so f is equal in this case to 0.2, so I'm writing 0.2 times the area of the segment. So area of rectangle is 2k plus 0.2 times the area of this segment is the fourth part, 1/4 times the area of the total circle, and this is 1/4 times pi. So plugging the value of k will give the value of this probability, the probability that xy were both positive. Okay, so if we will move back, describe where the values of xy can be, so possible values of xy. So what I mean by that, well, I mean our f, the joint PDF, is 0 here, 0 here, 0 here, 0 here, 0 outside of these two portions. If I will generate random numbers from, well, random points, in fact, not numbers, random points from that distribution, my points will be either in this circle or here. So if I will generate points, I will get either points here or points here. So I will not get points outside of that two regions. So that was the idea of that question. So describe where the values of xy can be. And the other part is about generation of random points from the distribution in R. Okay, maybe I will describe this with a separate video. After this video, I will record that part, how to generate from two-dimensional distributions like this. I will give that soon separately. Okay, so let me move here, erase everything, move back, and talk about this knot. So here we were asked to calculate the probability that x is larger than 0 and y is larger than 0. So please note that in general, this is another common mistake people are doing. So in general, the probability that x is larger than a and y is larger than b is not equal to 1 minus probability that x is less or equal than a and y is less or equal than b. Why is that? Because the probability that x is larger than a and sorry, and y is larger than b, if I will pass to complement, I will have the following. 1 minus, this is not correct. So here I have x is larger than a and y is larger than b. The negation of that will be either x is less or equal than a, or here I'm not writing and, but I'm writing or, sorry. Let me erase. or y is less or equal than b. So the negation of and is or. So probability that x is larger than a and y is larger than b is equal to 1 minus probability that x is less or equal than a or y is less or equal than b. And if you want to calculate this, recall that formula for the union of two events. So you can calculate this if you want by writing 1 minus the probability that x is less or equal than a plus the probability that y is less or equal than b and minus the probability that x is less or equal than a and y is less or equal than b. So this is the correct formula if you want to write this in the complement form. Okay. Let's move forward. So the next question is the following. Problem is the following. So f is given in the following form. So f is this function over the rectangle 0, 1, 1, 2, well, square 0, 1, 1, 2. So x is between 0, 1, y is between 1 and 2. F is this function and 0 otherwise. Show that f is legitimate joint PDF. So to show this, I need to have that f is non-negative. Well, f is non-negative, of course, because here x and y are non-negative. This is non-negative and 0 otherwise. And I need to check that the double integral of f over R2 is 1. So double integral of f over R2 is just the double integral of f in this square. So let me show that double integral of this function is 1. So I'm doing that. So double integral over 0, 1 times, well, that was 1, 2, yeah. Of the function 1 over 3, 1 plus 4x squared y dx dy. So because I am dealing with rectangle, I can write first x is from 0 to 1, then y is from 1 to 2, or vice versa. So I'm using first integration in terms of y in this case. So y is changing from 1 to 2, so dy. Then for each y, so I have rectangle 0, 1, square, sorry, 1, 2. Well, I have this rectangle. This is the integration region. So I'm describing that in the following way. I'm fixing y. So this is y. Y is running from 1 to 2. And for each fixed y, my point inside, for my points inside that square, x will go from 0 to 1. This is 0. So I'm writing from 0 to 1 of our function 1 over 3, 1 plus 4x squared y dx in this case, because I have already integrated with respect to y. Okay, so first I'm calculating the inner integral. So here y is fixed. And I'm integrating with respect to x. By the way, this constant will go out, 1 over 3, integral from 1 to 2 dy. And here I need to integrate this with respect to x, so I'm getting the integral of 1 is x, the integral of this is 4 over 3 x cubed y, and I need to plug x is equal to 0 to x is equal to 1. So this is equal to 1 over 3, integral from 1 to 2. I'm calculating the value of this. First plugging the value x is equal to 1, I'm getting 1 plus 4 over 3 y. Yeah, 1. And then minus, I need to take out the value at 0, but the value at 0 will be 0 here, 0 here, so 0. so no need to write that. dy. Now it is easy to calculate this integral, so I will have integrating with respect to y plus 2y squared over 3. So y squared over 2, I will cancel that 2, and y is from 1 to 2. And this will give 1 over 3 times 2 plus, here I will have 8 over 3 minus 1 minus 2 over 3. So 2 minus 1 will give 1, so 1. 8 minus 2 will give 6. 6 over 3 is 2. 3 over 3 will give 1. So I will have 1 in the integral, so this function is a legitimate PDF. So I'm erasing this, going back to our problem. So calculate the probability that y is less or equal than 1.2. So graphically, I'm drawing again a two-dimensional version of that. So 0, 1. First I am drawing the support, so-called support, the set where f is a non-zero. 1, 2, so I will have this square. So our f is non-zero here. F is given by that formula 1 over 3 times something, and f is 0 outside this square. So f is 0 everywhere else. And we are asked to calculate the probability that y is less or equal than 1.2. So y is less or equal than 1.2 means we need to calculate the probability that our point is inside that horizontal line passing through 1.2. So we need to calculate the probability that our point xy is here. But because our point xy cannot be in this region where f is 0, it remains to calculate the probability that our point xy is here only, in this portion. So because f is non-constant here, I cannot calculate by just calculating the height times the base area. So I need to integrate my function f over this region. So this is a, if I will denote that by a, this rectangle, then I will have the probability that, let me write, maybe erase this and write in black or blue. So I'm calculating the probability that y is less or equal than 1.2. This is the same as to write the probability that xy is in this region A, the rectangle A, and this is exactly the probability, the integral over A of x, fxy dx dy. And this is equal to, I need to describe that rectangle A. So rectangle A is the rectangle x is moving from 0 to 1 and y is moving from 1 to 1.2. So I will describe again first by y. So y is running from 1 to 1.2 and this is dy. And then for each y, for the points inside this A, I will have x is running from 0 to 1. So from 0 to 1, our function f, and inside this region, our function f has the following form: 1 over 3, 1 plus 4x squared y dx. So it is easy to calculate. First you are calculating this integral, then plugging that function of y here and calculating the outer integral. I will not calculate, so please continue and obtain this value. Okay. So calculate the probability that y is larger than 1 plus x squared. So let me write in the form of an integral, and then I will leave the calculation to you. Okay, so I'm erasing this part, doing that graph again. So this is x, this is y, the region where our function is not 0, y 1, 2, and this was that square. So here the values of f are non-zero, and otherwise our function f is 0, our PDF is 0, so xy cannot be there, xy can be only in this region. So the problem was asking to calculate the probability that y was larger than 1 plus x squared. So I am drawing first the line y is equal to 1 plus small x squared in this domain. Then I am taking the upper part to obtain y is equal to 1 plus x squared. So y is equal to 1 plus x squared will have the following form. So this is the parabola raised by 1 unit. So parabola, something like this, raised to 1 unit. So I will start from this point. If x is 1, if I will plug x is 1, I will get 2 here. So y is 2. So my parabola passes through this point. So if x is 0, y is 1, x is 0, y is 1, x is 1, y is 2. So I will have this kind of parabola and some other part here. This part is not necessary. So I will take the upper part of that parabola, so upper part, and because f is 0 outside of this rectangle square, then I will have only this portion to calculate. So if I will denote this by a, then this probability is the same as calculate this probability, the probability that my point xy will be in this region A. And that probability will be the following: double integral over that a of f dx dy. Now I need to describe that a, region A. Let me first describe in terms of x then y, this green shaded region. So for this point, 4 points in that A, x is running from 0 to 1. X is running from 0 to 1, so dx. And now I need to write y, where y is running. So if I am fixing x, so this is x, for that x, the points inside our region A will be from this point. By the way, the equation of this line is y is equal to 1 plus x squared. 1 plus x squared. So this point will be 1 plus x squared exactly, and this point is 2. So y is changing from 1 plus x squared to 2. I need to write the equation of f, and inside this region f is 1 over 3, 1 plus 4x squared y dy. Okay, so you can calculate this integral, but I want to write, I do not want to calculate, but write in the inverse order. So first in terms of y, then in terms of x. So first I'm again describing this region, green region, first in terms of y, then in terms of x. So y is running for the points of this region, y is running between 1 and 2. So y is running between 1 and 2. Now I need to write where my points x is running. So if this is y, I am fixing y. Then x is running from this point, so this is 0, x is 0, to that point. How to find this? I need to solve this for x. So that will give x squared is y minus 1. And because x is positive, we are talking about positive axis, x is between 0 and 1. So x will be the square root of y minus 1. So this point is exactly square root of y minus 1. So let me write x is equal to square root of y minus 1. So I'm solving this equation for x. So x is running from 0 to square root of y minus 1. I'm again writing the same function, 1 plus 4x squared y dx in this case. So you can try to calculate either this using this form or using that form. Okay, I'm reversing this and moving back to our problem. So on the next few slides you will find the graph of f. So I'm drawing that graph in three-dimensional space, and we have random sample generated from this distribution, random variate generated from that distribution, and some visualizations. I will explain that visualizations. And the problem is asking to generate in our random sample from this distribution. So I will do that with a separate video. Okay, so I'm erasing this, I'm moving to the next slide to show the graph of this and some points generated from that and some visualizations. Okay, so this is the joint PDF graph. So you can see that, well, this is the x-axis, this is the y-axis, or here, the y-axis. X is between 0 and 1, y is between 1 and 2, and otherwise f is 0. So this surface is 0, surface coincides with the XOY plane, except this portion, and in that portion our surface has this form. You can see that the chances that my points xy will be here are smaller than the points will be on that corner, close to that corner, with point 1 and y is 2, x is 1 and y is 2. Okay, so to check this I'm generating by using that r some points. So these are my points generated from that distribution. You can see that here I have dense points, so the probability that my points will be here are high, and the probability that my points will be here were small. So I have few points here, more points here, concentrated here, because the value of our joint PDF is higher here. So if we will take two equal area portions here or there, the volume under the PDF will be higher here, so the probability is higher here. Okay, so what I'm doing, other kind of visualization. So this is called heat map. So we are doing, in some sense, histogram. So histogram, but we are not writing the not doing that in three-dimensional space, but some kind of two-dimensional space. If the number of points are high, we are drawing with light blue. If the number of points is small, then we are doing in dark blue. So you can see that here we have a lot of points. The count is showing how many points are in this small rectangle. So light blue here, so more than 50 points are here, more than 50 points are here, no points may be here, small number of points here, small number of points here. So this is called the heat map. I have another version of that heat map, sorry. This is another version. Well, heat is high, so the number of elements are high here. So number of generated, I'm generating some points from that distribution, the same distribution. So I will have small number of points here, small number of points, and high number of points at this corner. So this is the number of points. Blue is cold, so not so many points, and that red is a high temperature heat map, so high heat. So many points are here. So this is showing some kind of dynamics. So how many points we have in different regions. Well, sorry. This is another type of, so this is hexagonal heat map with hexagons, not rectangles. The same thing. high number of elements is in yellow, sorry, and the low number of elements is in blue. Okay, another thing, well, I can do that exactly 3D histogram. So you can see histogram is showing how many elements are in the in each individual rectangle. So we are dividing our XY axis into small squares or rectangles maybe, and calculating, generating points from that distribution given by that joint PDF, and calculating how many elements are falling into each rectangle and doing bar over that rectangle with that given height. Height is the number of elements, number of points generated in that rectangle. So we have a lot of points in that small rectangle. We have many points here, but small number of points in this region. So this is this 2D, 3D maybe histogram is giving approximation for that shape of the joint PDF. Okay. Now the next problem. So XY is a random vector with the joint PDF given by this. So in this case, our domain, well, support of F, where F is non-zero, is not rectangular. So this is half of the, not the half, but quarter part of this circle. In that quarter part, F is k times x times y, and we need to find k and then calculate some conditional probability. So to calculate k, we need to solve the following. So I need to have 1 is equal to double integral over R2 of f dx dy. And because f is 0 outside of this region, so let me first, maybe it is better to start with that region. So this is x, this is y. So we will have x squared plus y squared is r less, the sum is less than 1. So this is 1, this is 1. This is a portion of a circle, unit circle, and x and y are positive, means we are in the first quadrant. So this is where our f is non-zero. So f is given by k times x times y in this region, and f is 0 otherwise. So I will not consider all other points. I will work only in this region. Okay, so I need to write the double integral over this, say this is d over that d of f dx dy. And to describe that d, I can do two things. Either I can write in the iterated integral form, say first x. So I'm describing first method, then I will do that in polar coordinates form. So first I'm writing the x. X is running from 0 to 1 in my region D. From 0 to 1 dx. And for each fixed x, if I am fixing x, for the points inside that D, y is running from this point to that point. So this point is easy, y is running from 0, and that point is easy again because the equation of this curve is x squared plus y squared is equal to 1. So this boundary is given by this. So I need to solve to find y. Y squared is 1 minus x squared. So y is equal to square root of 1 minus x squared. And because y is positive, I'm putting plus sign, so no need to add any sign here. Because I have two solutions from here, I need to take the plus sign part because y is positive for this portion of circle. Okay, so y is changing from 0 to this point, and this point is 1 minus x squared of our f, and f is k times x and y in that region, dy. So we can calculate this, easy to calculate because we will have y squared. If we will plug this, this will be squared and we will not have any square roots. We will calculate this easily. Okay, I will not calculate. I will assume that I have already calculated that k. And you will find this k from this equation. 1 is equal to this. Okay, I want to write, give another method to calculate this integral by passing to polar coordinates. So what I'm doing the following. So passing to polar coordinate, x is r cosine phi, y is r sine phi, and the Jacobian in absolute value is equal to r. This is for polar coordinates. Now I need to describe my region D, this is D, in polar coordinates. So it is easy to describe this because this is a circular region, circular shape region. So r is changing in this region, r is changing. The distance between that point and the origin is from 0 to 1. So if I will take any point, this r will be between 0 and 1. So r is changing from 0 to 1 dr. And for each fixed r, so if I am fixing r, this is r, I'm getting something like this. All points with distance r from the origin, then only the portion where phi is between 0 and pi over 2 will be inside my D. So phi is running from 0 to pi over 2. And here, instead of f, in f, I need to plug, instead of x, r times cosine of phi. Instead of y, I need to plug this, and I need to multiply by the absolute value of the Jacobian. So I'm writing k times r cosine phi for x times r sine phi for y, and I'm writing the Jacobian d phi. So it is again easy to calculate because k is constant, that will go out. R, these are constant for this inner integral. So this integral is with respect to phi. We can calculate that integral easily. Say, take that sign into the d sign, you will have cosine, d cosine with some sign, and you will left with some integral with r squared dr and some constant. Okay, so two methods to calculate that k, that integral, giving the value of k. Okay, so I'm assuming that I have already that k. I'm erasing everything here, and I'm calculating this probability. So again, I'm first writing the definition of that conditional probability. So I'm writing that probability in the following form: probability that y is less than 1 minus x and x is less than 0.5, and over the probability that x is less than 0.5. Now the geometry, what are we calculating? So this is x, this is y. I have the region is this portion, this segment, one here, this segment. We are working inside this segment, and we need to calculate the probability that y is less than 1 minus x, x is less than 0.5. Okay, maybe it is first easier to show how to calculate this, then I will draw this region too. X is less than 0.5, so this is 0.5. X is less than 0.5 means we are on the on the left to this 0.5. So if I will draw that, maybe I will take another color. So we need to calculate the probability that our points are in this region. So if I will denote that by A, these are the points that can happen, and the coordinate x is less than 0.5. What I mean by that they can happen, so because f is 0 here, 0 here, 0 here, so the points here cannot happen, so only this part remains. So probability that x is less than 0.5 is the same as probability that my point xy is in that green region A, and this is exactly double integral of our f over A. And for A, our f is k times xy. We have this value of k now, dx dy. And to calculate this, we can just write the iterated integral form. So iterated integral will give, so x is running from 0 to 0.5 dx. And for each x, if I am fixing x, so my y is running from this point to that point. So y is running from 0 to this point is, again, because this equation is x squared plus y squared is 1. We are solving for y. We are getting y is equal to, with positive sign, square root of 1 minus x squared. Y positive because y is again above this line, so y is positive. So square root of 1 minus x squared of our kxy dx dy, because we have integrated already in terms of x. So this integral will give the probability that x is less than 0.5. So this denominator we can calculate in this form by using this. So now I am erasing this and writing how to calculate that numerator. Okay, so we are calculating the numerator. Okay, so what is giving that numerator? Y is less than 1 minus x. 1 minus x, so I'm drawing the line, y is equal to 1 minus x. So this is the line passing through this point 0, 1 and 1, 0. So you can check that it is passing through these points. So if I will draw, I will have this line. Well, maybe I will take another color. Yeah. So this is the line with the equation y is equal to 1 minus x. And because we have y is less than 1 minus x, we will have the portion under this line. So under this line and x is less than 0.5. So I will intersect this set with that set and with the support of this function. So with this set. So I will have just this trapezoid for that. And if I will denote that by b, this set by b, then probability that y is less than 1 minus x and x is less than 0.5, this will be the probability that my point xy is in that b. And this is the double integral over b of f dx dy. So how to calculate this double integral? Well, again, by bringing to iterated integrals form, say in the order of first x, then y. X is running in this region. X is running from 0 to 0.5 dx. So, and y is running for fixed x. So this is x, say. For fixed x, my y will run from this point to that point inside that region B. So I'm writing here y is running from 0 to this point, and this point equation is given by y is equal to 1 minus x. So 1 minus x. F is here k times xy dy. So calculating this integral will give this probability, and dividing by that probability you will get this conditional probability. Okay, so let's move forward. Now about marginal PDFs. Assume we know the joint PDF of x and y, so we know the joint distribution of random vector xy. Here our aim is to find individual PDFs of x and y called marginal PDFs. So I know the distribution of this point, this vector. I want to find separately how x is distributed and how y is distributed. So this is easy. In fact, it can be proved that if our xy is a continuous random vector with PDF fxy, then x separately and y separately are both continuous random variables, and we can calculate the PDF of x by integrating our joint PDF with respect to y. So we are integrating out that variable y, so integrating over the real line with respect to y, obtaining some function of x. This is our marginal PDF for x. And if I want to find the marginal PDF of y, then I'm integrating out the variable x. So I'm integrating from -infinity to infinity fxy dx for any y. Okay, geometrically we are doing the following. So this is the joint PDF surface. So what we are doing is the following. So what are these? These are the graphs for marginal PDFs. And how we are obtaining these marginal PDFs, we are not just projecting this. We are doing the following. So say to calculate the value, what is the value of this marginal PDF? So to calculate that value, I'm doing the following. So I'm considering all points over this line. So I will have the shape, this is the shape of my surface over this line. So think like this. I'm taking a plane passing through this line and orthogonal to x or y. So I am taking this plane passing through this line, and I'm obtaining some cut, some intersection line with this surface of joint PDF. Say this is that intersection line. And I'm calculating this area. In fact, I'm fixing, say this is x, I'm fixing x, and integrating with respect to y. Say this is y, this axis is y. Integrating with respect to y, that is, I'm calculating this area of that cut, of that intersection with the plane passing to this line and orthogonal to x or y, perpendicular to x or y. Okay, and this area is the value here. So if I want to calculate this value, so I'm considering a perpendicular plane passing through this line. So I'm fixing the value of y. Then I'm obtaining some intersection with this surface. The intersection surface will be something like this. And I'm calculating the area under that intersection line. And this area will be here. The value of this function, well, marginal PDF will be this area. Hope this was clear. Okay. So moving forward, this is almost the same explanation, but not with the theoretical joint PDF, but I'm doing the following. So I'm generating random points from that distribution, joint distribution. So I will have this kind of points. So concentrated here because the volume was high at this point, close to the some kind of center. Here the volume was high. A few points here away from that center, say I will have something like this. Now what I'm doing, I'm calculating all point projections. Say this is a point. I'm calculating the x coordinate of that point. This is another point, I'm calculating x coordinate. This is another point, I'm calculating x coordinate. So on the x coordinate, I'm calculating all points, all my points, x coordinates. So I will have a lot of x coordinate here and few x coordinates. Say this will be the x coordinate for that point. This will be just one point here. Now I will have a lot of points here and few points here. Then for this x coordinate, I'm doing the histogram. So how many points are lying in this interval? How many of them are lying in this interval? Of course, I will have a lot of points are in this interval. So the height of this histogram will be high here. And few points here. So few points with x coordinate here. So I will have small histogram value here. So I will have this kind of shape for my histogram. So this histogram is approximating the shape of the marginal PDF for x. And I'm doing the same for y. So what I'm doing, I'm calculating the y coordinates for all points. Say this is one of the y coordinates. This is one of the y coordinates. I will have a lot of y coordinates here, a lot of points here. So here. Then I'm doing the following. I'm dividing into bins and calculating how many points are here. And I'm drawing that height here. So if I have 100 points, so this height will be 100, 150, say 200, etc. So I will have this histogram, and this histogram is showing the shape of the, approximating the shape of the PDF of y, so marginal PDF of y. So this is with generation, with random variate, with generated random, well, maybe not numbers, but points to the random points. Better to write random points in marginal histograms. Okay. Let's move forward. So, example. Assume xy is a continuous random vector with joint PDF given by k times x plus y in this square. Xy is from 0 to 2 and 0 otherwise. So find k. We know how to find k. To find k, we need to write. I will not solve that find, but let me write the equation. So I'm writing the following. So 1 is equal to the double integral over R2 of f dx dy, and because f is 0 outside of this, I will have only integration over the, this is x, this is y, over the square 0 to 0 2 over the square only. This is 2. So I will have x is running from 0 to 2 dx, y is running from 0 to 2. Our function k times x plus y dy. So from here, from this equation, we will find that unknown value of k. I'm erasing this. So second part, calculate the probability that y is equal to x squared. So even I am not writing, I'm not drawing the joint PDF support where f is non-zero, but I know that the I want to calculate the probability that my xy point is here. Xy is on this curve. Because we are dealing with continuous random vector, well, we have joint PDF, that means that we have continuous random vector. Then this probability will be 0. The probability that point xy will lie on a curve, on this curve with area 0, will be 0. So nothing to do here. Okay, calculate the probability that y is larger than x. Here we need to do something. So this is x, this is y, support. So 2, 0, 2. This is the support. So what I mean by support, f is non-zero here. So f is given by this formula here, and f is 0 outside of that. Okay. Now I want to calculate the probability that, let me, maybe I will make something like this. So here f is non-zero, outside is 0. Y is larger than x. So I'm drawing that region and taking the intersection with this support. So y is larger than x. First I'm drawing that y is equal to x. Then I will take the upper part because y is larger than x. Y is equal to x is this bisector, and y is larger than x will be upper part of this, and the intersection with this support will give this portion. So this is our A, and probability that x, maybe I will write, I will write in blue, probability that y is larger than x is just the probability that my point xy is in that A, in this triangle. And if I want to write in the iterated form, I will write the following. Say first x, then y. Say x is running from 0 to 2 inside this region, 4 points inside that region, 0 to 2 dx. Now for fixed x, I'm considering all points with coordinate x, first coordinate x. So I'm getting this line, and only this portion is inside that region A. So that portion will be, I need to find this point, this value of y, this value is 2, from this to that. And how to find that? I know the equation y is equal to x, I'm solving for x, so x is equal to y. So y is running from x, well, that was given, no need for this. Y is running from x to 2. So from x to 2. Here I need to write our f. F is k times x plus y dy. So this is the probability that y is larger than x. Okay. So the next part, calculate the probability that x squared plus y squared is less or equal than 1. Again, first geometrically, what are we calculating? So xy is in some region. I need to draw that region, then write double integral for that. So this is our support 2, 2. So our f is non-zero only here. And we need to calculate the probability that x squared plus y squared is less or equal than 1. That means that our point xy is inside unit circle. So unit circle is something like this. I'm not drawing the other part because I need to intersect with this support. So I'm getting only this part. So this is my A for the part D. So I'm writing that this integral, this probability is the same as probability that my xy is in A, and this is equal to integral of f over A dx dy. Now how to calculate this integral? Again, I will use polar form because my A has some circular shape. Okay, I need to describe this region A by using polar coordinates. For points in A, r is changing from, well, let me write that. I'm using x is equal to r cosine phi, y is r sine phi, and the Jacobian is r, so the absolute value of Jacobian is r again. So r is changing from 0 to 1 dr, and for each r, phi is changing from 0 to pi over 2. My function was k times x is r cosine phi, plus r sine phi, this is y, times r, this is the Jacobian, and I need to integrate with respect to phi, d phi. So this integral, the value of this integral will give the probability. Okay. Now, find the marginal PDFs of x and y. So this is important, so I want to calculate this marginal PDFs. Well, I will not obtain in the final form because I need to plug the value of k, but I will obtain in terms of k. So marginal PDFs of x and y. I will do that for x, and because everything is symmetric, I mean the function is symmetric and the region is symmetric with respect to x and y, I will get the same for the marginal PDF of y. So I'm doing for x. So I'm erasing this and passing to the whiteboard. So my f is fxy is k times x plus y inside the following. So if x and y are both in 0, 2 and 0 otherwise. So and I need to find the marginal PDF for x. So I'm drawing again that always draw the figures. You have the support and the integration region. So support is 0, 2, 0, 2, so this square, this is 2. So this is our support, where f is non-zero and everywhere else our f is 0, joint PDF is 0. Now what we want to do, we want to calculate fxx. So the marginal PDF for random variable x. This is capital X, this is small x, at the point small x. Okay, what I'm doing, I'm remembering that I need to integrate out the variable y from the joint PDF. So I'm integrating from minus infinity to plus infinity the joint PDF with respect to y. So this is the general formula. Now I need to calculate this for my particular case. So I need to consider different values of x. So for different values of x, this will be different. Say if x is here. So if x is here, I'm integrating over y. So that means x is fixed, and I'm integrating over this line over y from minus infinity to plus infinity. What I'm integrating? I'm integrating my f. So I'm integrating f. So because my f is 0 here everywhere on this line, so the integral over this over this line will be 0. If my x is here, I'm fixing x and integrating my f with respect to y. So I'm calculating the integral over this line. Then again I will get 0 because my f is 0 there. So f is 0 everywhere on this line. So at the end I will have this is 0 if my x is not in 0, 2. So for all points x outside of that 0, 2, I will integrate over this line, I will integrate 0. This is 0. Now interesting thing is when x is in 0, 2. So if x is in 0, 2, I'm writing the marginal PDF of x at the point x is again this integral. So fxy dy. So what I'm doing in this case, so I'm doing the following. Now x is here, and I'm integrating over this line, the whole line, passing through that point x and parallel to y. So I'm integrating over this line, my f. But my f is 0 in this portion, so let me take another color. F is 0 here, f is 0 here. So I will be left with the integral from y changing from 0 to 2. So only in this green part. So I'm writing this is equal to the integral from 0 to 2. Y is changing from 0 to 2 of my f xy dy. And now I can plug the value of that f. So I am integrating from 0 to 2 k times x plus y with respect to y. And I will have k times the integral of x with respect to y. So x is constant here, xy plus y squared over 2. And substituted y is, let me write that y is changing from 0, y is 2. I'm plugging first the value 2 I will have k times 2x plus 2 here, minus the value when y is 0, but if I will plug y is 0, I will get 0, so nothing to plug here. So finally, I can write the formula for my f. So the formula will be for the marginal PDF of x will be the following. It is equal to k times 2x plus 2 if x is between 0 and 2, and 0 otherwise if x is not in 0, 2. So this is the distribution PDF, in fact PDF of random variable x. Okay, so similarly, if you will change x to y, here you will write say y, you will obtain the marginal PDF of y because of symmetry of function and symmetry of the region. So we have solved that part E. Now F part. Calculate the probability that x is in 0, 1. So why I'm writing this, we have met these kind of problems because we can solve this problem in two ways. So the first method to solve F is the following. We have obtained this PDF of x. So I can write the probability that x is between 0 and 1 is exactly the integral over 0, 1 of that fx dx. So I have the value of this PDF. I can plug, integrate, and obtain. But I can solve this without calculating the marginal PDF. So let me do that in second way. So I'm erasing this and solving this by using just the joined PDF. So again, I'm drawing that graph. Support. So 2, 2. This is 2. This is 2. F is non-zero here and 0 otherwise. So x is between 0 and 1. So this is 1. So x is between 0 and 1, and y is arbitrary. That means that we are talking about this region. So x is between 0 and 1, y is arbitrary, and we need to intersect with this support, with this square. We will have just this. So the probability, let me write in blue, the probability that x is between 0 and 1 is the same as probability that my point xy is in A, in this rectangle. And now I can use double integration over A to calculate that probability. And this will give, if I am integrating this over A, for A, x is changing from 0 to 1 dx, and for each fixed x, y is changing from 0 to 2. 0 to 2, and f is k times x plus y dy. So if you will calculate this, you will obtain the same as in the other method, in the previous method. Okay, now calculate the PDF of random variable z is equal to y minus x. So I will not solve until the end. I just want to give the idea how to calculate that. Okay, z is equal to y minus x. Again, the region. This is y. This is 2. This is 2. Okay, in this region, our f is non-zero. F is given by, let me write, f is equal to k times x plus y here, and 0 otherwise. Okay, so our problem was to calculate the distribution, the PDF of y minus x. How to do that? First, I'm writing the CDF of z at some point z, say. This is by definition the probability that z is less or equal than that small z. A random variable z is less or equal than z. Now I'm plugging the value of z. So y minus x is less or equal than that z. Now I need to calculate this probability for any z, any value of z. To calculate this probability, well, I need to draw geometrically the region over which we are integrating, or region where my point xy is lying. So I will have something like this. So let me draw this region where y is less or equal than x plus z. So to that end, I need to draw the line first. First, I need to draw the line where y is equal to x plus z. Then I will take the lower part, the part under that line. Well, to draw that, I need to consider several cases. Say, first case is when z is less than -2. So let me draw this case. So I will have, let me continue this. Well, I will erase this. P. Yeah. Okay, say z is here. If I will draw that line y is equal to x plus z, z is less than -2. I will have this kind of thing. So this is the equation of y is equal to x plus z. Say x plus -10. So x minus 10, this is the equation of y is equal to x minus 10, say. Okay, and we are interested in the probability that y is under that line. Y is less or equal than x plus z. So because we do not have intersection with this, we need to integrate 0 in this region, in this portion, then we will get 0. So in this case, I will have, if z is less than -2, then fz at the point z will be 0. Okay. Another case is when z is larger than 2. So why I am taking this -2, you will see that. Okay. First, the region. So I am forgetting this. So I will not erase. And now I am drawing y is equal to x plus z for z that is larger than 2. Say z plus 3, z plus 4. Then I will have this kind of shape. So this is the point z. So if x is 0, y is equal to z. So it passes through the point z. And I am calculating the probability that my point will be under this. Of course, that is the probability that my point will be inside this square. And the probability that my point is inside this square is 1, just. Because my point will be only in this region. F is 0 outside. So in this case, I will have fz at the point z is 1. Okay, what will happen if z is between -2 and 2? So I need to consider two cases. If z is less than 0 and larger than -2. What will happen in this case? So in this case, I will have the following shape. So z is negative between -2 and 0. So z is here. Say this is -2. Z is here. So the line y is equal to x plus z will pass through this point. So I will have this kind of graph for this line. And I need to take the lower part for this line. So and intersect it with the support, with this square. So I will have this portion. By the way, this point will be, this point will be minus z. Well, this length is, this height maybe, this height is absolute value of z, or minus z. Z is negative, z is negative. So this length will be minus z. So I need to integrate my function f in this region. So I'm writing that. So in this case, fz at the point z is this probability. So this is the integral, double integral over this portion, and I want to bring to the iterated integrals. So x is running from minus z to 2 dx, and now y is running. So if I am fixing x is here between minus z and 2, and then y is running from 0 to this point, and that point, because the equation is y is equal to x plus z, this point will be just x plus z of our function small f, which was k times x plus y, k times x plus y dy. So calculating this, we will obtain some function of z, and that is the value of fz in this region. Now, why we are separating into two portions that that interval between minus 2 and 2? Because on the other case, if z is between, so the remaining part is when z is between 0 and 2, and in this case we need to calculate fz at the point z. So this is the probability that y is less or equal than x plus z. In that case, we will have the following picture. So z is positive between 0 and 2, say this is z. I will take this line, which is x plus z again, but for this z, and I need to integrate over this region. I need to consider the region under that line and in that support, in that square. So I'm integrating over this. Okay. Maybe I can write in this case, this is equal to, let me erase all other things. So I'm erasing all other things we have calculated for this case. That it remains to calculate for the case when z is between 0 and 2. And I am writing that in the following way. Say this is equal to 1 minus the probability that y is larger than x plus z, and this is equal to 1 minus, now I need to integrate over this portion, say over this portion, remaining part, and I can write that in the following way. So integral from let me describe in this case in terms of first y, then x. So y is running from z to 2, so y is here. From z, let me erase and write it clearly. So from z to 2 dy, y is running there. So for each fixed y, x is running from this to that point. So this point is 0, x is running from 0 to how to find the value here, value of x here. So I'm solving this with respect to x, in terms of x. X is equal to y minus z, so I will have y minus z. And I'm writing my function k times x plus y dx. So having this integral, the value of this integral, we will have well, let me recall that this was fz at the point small z, where z was between 0 and 2. So we will calculate the CDF fz for all points z. Then calculating the derivative of this fz, we will obtain the PDF of z. Okay. So let's move forward. The next is the following, another example. Assume that the joint PDF of x and y is given by this formula. So in this case, I have infinite sum region. So let me draw that. Something like this. This is x, this is y. The support is this half strip. So x is between 0 and 1. And y is non-negative. So x is between this and y is non-negative. I will have the following. So xy is here. So this is the support of our function. So f is given by this formula here and 0 outside. So find the value of c. To find the value of c, we need to have the double integral of f dx dy over R2 is 1. So this can be written, we just need to take this the integral over this region, red region. So I'm writing the integral from 0 to 1, x is from 0 to 1. And for each x, so dx, for each x here, if this is x, my integration over y will be from 0 to plus infinity. So y is changing. So y is changing from 0 to plus infinity for any fixed x. So I will have from 0 to plus infinity c times x times e to the minus y dy. So it is easy to calculate this integral because integration of e to the minus y is easy. So you will find c easily, the value of c easily from this equation. Okay, so let me erase this part and calculate the b part. Solve this b part. B part is about calculation of some probability. So probability that y plus x plus y is less or equal than 4. So I'm writing this region and the intersection of this region with my support, this red region. So okay, so y is equal to first I'm writing y is less or equal than 4 minus x. Then I'm considering this line y is exactly equal to 4 minus x. So if x is 0, y is 4. So this is 4. So if x is 4, y is 0. So this is 4. So we have this line. Joining these 2 points, sorry. Yeah. And because we have y is less or equal than 4 minus x, I have the lower part to this, so the points under this line, and we are intersecting that with our support and we are getting this portion. So this is our a, and I need to write the probability x plus y is less or equal than 4 is exactly equal to the double integral over a of our f dx dy. And now I am describing that a in terms of iterated integrals. So in a, this green part is our a, x is moving from 0 to 1, so 0 to 1 dx. And for each fixed x, say this is our x, let me change the color. For fixed x, inside our region a, y will change from this point to that point, while y will run from this point to that point. So this point is 0, so I'm writing 0. And to find this point, well, I am remembering the equation, and the equation is 4 minus x. So if this is x, this is 4 minus x, 4 minus x. So I'm integrating from 0 to 4 minus x. My function c times x times e to the minus y dy. So it remains to calculate this integral. We have that value c from the point a, from the part a. So we will obtain some number here. Okay. Now let me erase everything and solve c. Well, not to do the whole calculations, but show how to find the distribution of random variables z, which is x squared plus y squared. Okay, again, I'm starting from the support. So this is 1. The support was this half strip. This is X, this is Y. Okay. F is our joint PDF is non-zero here and 0 otherwise. So we are talking about the distribution of this. So I am starting again, everything is starting from the CDF, joint CDF, not joint because this is one dimensional random variable, from the CDF of Z. The CDF of Z at the point small z. This is the probability that our random variable Z is less or equal than that small z. And this is by definition of Z, x squared plus y squared is less or equal than Z. So we can separate two cases. When Z is less than 0, well, this is 0, so F is 0. Fz is 0, of course, because we do not have points satisfying this. Okay, interesting is when Z is larger or equal than 0. In that case, we have we can write this as xy. The point xy is in disk with radius z. So this is the disk with radius, well, not z, but square root of z, sorry, square root of z. This means that our point xy is in the disk with centered at the origin and with radius square root of z. So let's consider two cases again. Separate this into two cases. So the first case is when z is between 0 and 1. What we will have in that case, if z is between 0 and 1, then the radius is less than 1. So we will have something like this. So this is square root of z. And we need to calculate the probability that our point is here. So f of z at the point z will be the integral of our f over this green region, over that green region. And I can write that in the following way. So I am bringing two polar coordinates. R is changing from 0 to square root of z dr. Phi is changing from 0 to pi over 2. My function is c times x, which is r cosine phi, times e to the minus r sine phi, times r Jacobian d phi. So if we will calculate this integral, we will obtain some function of z here. And that will be the value of fz if z is between 0 and 1. Okay, so let's see what is happening and why we are separating that part z is smaller than 1 and z is larger than 1. If we will have that, if we will have that z is larger than 1, so we will have that our radius of our circle disk is larger than 1. So we will have some portion of this segment. So in that case, let me erase this too. Say, in that case, we will have the following. Square root of z is here, is larger than 1. We have this portion. And we need to integrate over this intersection. So that intersection will give this. So we need to integrate over this portion if z is larger than 1. So we are not integrating over that because f is 0 here. So in that case f will be the following. Fz is, I need to integrate my f over this region. And now I'm integrating with respect to x. It is better to describe not in the polar coordinates form, but in x and y. So x is between 0 and y, dx, and y is changing for, this is x, y is changing from 0 to this point, and that point is found from the equation of this curve of this boundary. and the equation is x squared plus y squared is z. So I will calculate y is equal to, because y is positive, I am taking the positive root, so y is z minus x squared. So for this x, y is changing from 0 to this point, which is square root of z minus x squared. And I'm integrating my function c times x e to the minus y dy. Calculating this, we will obtain some function of z, and that is the value of our f for the part z is larger than 1. And having that CDF, we can calculate, say, the PDF of that z by differentiating this. Okay, you can finish this example and find the distribution of this random variable z. Let's move forward. Assume the lifetime of my desktop computer, HDD and CPU, so two parts, desktop computers, HDD, hard disk, and CPU, in years are jointly distributed with the joint PDF, these ones, for x, y are larger or equal than 0. So I will have this kind of shape. So I will have, this is x, this is y. My support is where f is non-zero, the set where f is non-zero. In fact, there is a mathematical definition of that support. Support is the closure of the set where f is non-zero. So this is our support where f is, this f is non-zero, and otherwise f is 0 everywhere else. Okay. What is the probability that my desktop will work no more than 1 year? No more than 1 year. So let age be lifetime of hard disk drive, and C will be lifetime of my CPU, computer CPU, and we want, if one of them is not working, of course my computer will not work. So we want to calculate the probability. I want to write this in mathematical terms. Desktop will not work more than 1 year. So if one of them will be less than 1, then I will not have working computer. So mathematically I am writing in this way. So if, say, h is less than 1, then I will have that hard disk is not working, so my computer is not working. So this is the mathematical statement of this question. So we need to calculate this probability. Maybe it is better for this case to pass to the complement. So 1 minus probability that minimum of h and c is larger than 1, and minimum is larger than 1 means that both of them are larger than 1. And now I can calculate this. So how to calculate only this? Well, later we can subtract from 1 that value. So to calculate this, I'm drawing this region. So this is, in fact, I'm changing the notations. This is h, this is c, this is 1, this is 1. So I'm considering the region when h is larger than 1 and c is larger than 1. So I'm obtaining this region to calculate this probability. So to calculate that probability, now I can integrate my function over this region. So I'm erasing this part and I'm calculating only that probability. Okay, so I'm calculating this in the following way. So probability that h is larger than 1 and c is larger than 1 is just the integral h is running from 1 to infinity, 1 to plus infinity, the h or the x is for h, and integral from for each x, if I will fix x in the domain, in my integration domain, y will run from 1 to plus infinity, independent on x. Every time for each x here, y will run from 0 to plus infinity, not 0, 1 to plus infinity, sorry, 1 to plus infinity. So x times e to the minus x1 plus y dy. So we need to integrate this to obtain this probability, and we will calculate 1 minus this probability to obtain the requested to answer to this question. Okay, moving forward. Well, assume fxy is the joint PDF of x and y, and we are asked to calculate the PDF of x plus y, so a general form. So let's solve this. So what I'm doing, I'm starting from the CDF of z, random variable z, at the point small z. Then I will differentiate this to obtain the PDF of z. So CDF is by definition the probability that z is less or equal than that small z. And because z is the sum, I'm writing y plus x is less or equal than that z. Geometrically, I have the following picture. So this is x, this is y. My function f is something here. Maybe it is non-negative everywhere, so I'm not drawing the support. I do not know what is the support of this function. This is general case. So I'm drawing this. So I need to calculate the probability of this. So I'm drawing where my xy point is lying. So xy point is lying under some curve line, and I want to draw that curve. So I'm drawing the curve y is equal to z minus x. So y plus z, this is the same, y plus x, sorry, is equal to z. I'm drawing this line, and I will consider all points under that line because y is less or equal than z minus x. So y is equal to z minus x is the following type curve. This is z, this is z. This equation is y is equal to z minus x. The equation of this line is. So we need to consider the case where y is less or equal than z minus x. So that means we are integrating over this region. So all points under that line. So this is A, this region is A. So I'm calculating this. This integral is equal to integral over A of fxy dx dy. So I'm writing it in the iterated integrals form. So 4 points in this A, x is running from minus infinity to plus infinity. Say the x coordinate of this point is this much, the x coordinate of this point is that much, x coordinate of this point is that much. So x coordinates are moving from minus infinity to plus infinity. Minus infinity to plus infinity, dx. And for each x, if I am fixing x, then y is running inside my A, running from minus infinity to this point. And this point is, well, y was z minus x. So y was z minus x. So y is changing from minus infinity to this point, z minus x. And here I'm integrating my fx y dy. Okay, I'm obtaining this. Well, I do not have f to integrate to calculate this value. Now what I'm doing, I'm calculating the derivative of this. So fz at the point small z is the derivative of this at the point z. So I need to calculate the derivative of this. So assume that I can take the derivative inside that integral. Under some conditions, I will be able to do that under some conditions on that small f. And by the way, this is not the only method to do this. You can do some change of variables here, two-dimensional change of variables, not polar to polar coordinates, but linear change of variables to bring to other form to be able to calculate the integral easily. But now I am doing without that. So I'm calculating, I need to calculate the derivative of this with respect to z. So I am calculating the derivative inside. So integral from minus infinity to z minus x fxy dy. This differentiated with respect to z. So z is only here. So I'm calculating the derivative with respect to z. And the derivative of upper limit integral will give the value of this function at that point. So because this integral is with respect to y, so the derivative of this integral will be the value of f at the point x. I'm keeping x, and instead of y I am plugging this, times the derivative of this with respect to z, which is 1. So I will have fx. Instead of y, I am plugging z minus x. Now I need to multiply by the derivative of this, which is 1, derivative with respect to z, of course, because I'm calculating the derivative with respect to z, and dx. This is dx. So this is the result. I want to write that here. So I'm erasing this part, unnecessary part. So we have obtained the following result. So the result is the following. The PDF of z at the point z is the integral from minus infinity to plus infinity of the joint PDF at the point x and z minus x dx. And we will use this later, this formula later. Okay. Now one note. From our last lecture, we know that if x and y are jointly discrete, then both x and y are discrete random variables. And we have calculated marginal PMFs from that joint one. So if x and y are discrete, jointly discrete, then x and y are discrete. And inversely, if x and y are separately discrete random variables, then this point xy or random vector xy will be discrete random vector. But this is not the case in general for continuous random vectors. So what I mean by that, above we have stated that if x and y are jointly continuous random variables, then separately x will be continuous random variable and y will be continuous random variable. So they both will be continuous random variables. But it is important that the inverse is not true in general. If x is continuous and y is continuous random variable, then it can happen that this pair xy is not jointly continuous random vector. So for example, if x is a continuous random vector, then the random vector xx, so y is equal to x, this random vector will not be jointly continuous. So you can try to prove this. Now that generalization for n-dimensional case, n-dimensional continuous random vectors. Say x is a n-dimensional random vector, column of vector. That's why I'm writing in this way. So a row transposed. We have defined the CDF of that random vector x by the following. So the value of our CDF at the point small x is bold-faced x, because x is a vector, n-dimensional vector. So it is the probability that our random vector is less or equal than this small vector. And what this means that x1, the first coordinate x1 is less or equal than this x1. Random vector x2, random variable, sorry, x2 is less or equal than small x2, etc. Random variable xn is less or equal than this number xn. So this probability is giving the value of our joint CDF. Now we say that our random vector x is jointly continuous if there exists a non-negative integrable function f of x, f of x1, x2, etc. xn of n variables, called joint PDF of x, such that the joint CDF is the integral of joint PDF over this region. So with respect to x1, we are integrating from minus infinity to x1. Maybe it is better not to write x1 here, so maybe u1, u2, un, f of u1, u2, un, instead of this, instead of that. And u1 is running from minus infinity to x1, u2 is running from minus infinity to x2, etc. un is running from minus infinity to xn. And x is that vector with coordinate x1, x2, xn. If there exists a function small f of this form, then we say that our random vector is jointly continuous, and this function is its joint PDF, n-dimensional joint PDF. Now, if x is jointly continuous random vector with joint PDF f of x, then for any set A in Rn, we can calculate this probability. The probability that vector n-dimensional vector x will be in that n-dimensional set A is that n-dimensional integral and tuple integral maybe over A of fx dx. And having the joint PDF of x, we can calculate marginal PDFs. So all coordinates xk will be continuous, and the marginal PDF of that xk will be calculated in the following way. So we are integrating all other variables out. So if, say, I want to calculate the marginal PDF of x1 at the point x1, so I am taking that joint PDF f of x1, x2, xn, and I'm integrating over all other variables. So x2, x3, xn, I'm integrating over minus infinity plus infinity minus infinity plus infinity n minus one dimensional space, so over n minus one dimensional space. Okay, this much for the main part.